This is a continuing webinar on the early modern drainage methods, including the development of the laser beam automatic depth and grade control system for the drain tube plow. And we first field tested this in 1966 at the Ohio State University. My original conceptual illustration of the projected laser beam for automatic grade control in the drainage plow is shown in this picture with a detector or a sensor mounted on the beam of the plow that's near the hitch point, and the laser beam unit projecting what I call a chopped laser beam, chopped it so that it would be modulated so that the sensor would be looking for a modulated or chopped light rather than a constant beam. That way it eliminated the interference from sunlight and so forth on the phototubes or whatever used in the sensor. This line was projected at a given depth or given height and parallel to the slope that you want to lay the pipe. Another view, closer view, where the original idea was to put this sensor closer to the hitch point and basically thought of moving the hitch point on that line that was parallel to at a given height and on the same slope as we want to lay the pipe. Turns out in my research on this that's not exactly right. I needed to move this sensor farther back, and that'll be explained in the webinar. This is a picture of one of the very earliest commercial units of the prototype laser beam. This is a helium neon gas laser. It was only 0.3 milliwatt power, very low power, but brilliant red light. It turns out that our experiments with this brilliant red light was carried out at Ohio State at about the same time, or really at the same time, as the first James Bond movie would come out, where they had tried to cut James Bond into two pieces with not a helium gas laser, but a solid state ruby laser. And everybody thought that Jim Faust was going to kill somebody with that laser around Ohio State. The picture of the laser transmitter with the shielding removed to show the telescope to enlarge the light beam and chopper blade to cause it to pulsate at a frequency of 150 cycles per second. This is the chopped 150 cycle laser beam projected through a 10 power telescope. We're doing it backwards. We're projecting the light through this eyepiece out the big end, which is I consider backwards of telescope, because using a telescope you're collecting light in the big end and focusing it to the small end. The purpose of that is by putting it through a telescope, it enlarges the beam, because coming out of here it's less than 1/4 inch in diameter, brings it up to about a 3/4 inch diameter, but it also collimates it. It doesn't diverge as quickly. So when you get out about 1,000 feet or so, the dot is probably around or less than 3 inches in diameter. 1,000 feet was farther than we normally would use this research model, but that was it. And we made a 5-slot blade here that would chop that beam up at 150 cycles a second. A close-up of the search prototype laser that consisted of 2 horizontal rows of closely spaced phototubes. These weren't photocells. At that time, we were not able to find photocells, although a few months later there were photocells or gelatins that would filter that helium neon gas laser light. But at the time, we couldn't find any photocells that were really sensitive to that red gas laser light. But we found some phototubes that were. But Those photo tubes were also sensitive to sunlight. So we buried them way back in what we call a black box. And here's the top row, bottom row. I think there were 7 photo tubes along there and 7 along there. And the idea was to balance the amount of, if the light was up here, the box moved up, it moved the hitch point up. If the light came down lower in here, the box was lowered on to be centered. So we even ran some tests where we drove this plow straight into the setting sun to see if it would be interfered. With being a chopped beam, the bright sunlight even got into back to the photo tubes, but it did not interfere with the grade control operation. So we're real pleased with that. The original circuit that Norm and I put together worked, but it wasn't very pretty. People that visited with us, some of our colleagues and some of our administrators wanted to see our circuits, and every time we opened a circuit box, the wires would come flying out, and it was a little bit embarrassing. And I remember telling Norm, I said, well, Norm, we got a way of making this thing work, but we sure we aren't very good at making it look pretty. And so we decided that we ought to find somebody that would help us make an integrated circuit. And I happen to know Mr. Ted Teach had a small firm, an electronics firm. He was an air pilot and had developed a guidance system for assisting pilots to land airplanes in the fog and at night. And he designed the circuit for us. This was put out on a government contract, and I never will forget the details of that. A lot of times a government contract has a way of, some firms say, oh, big government contract, and really elevate the bid. One of the firms over in Massachusetts, like a big electronic firm, bid $5,000 to develop and put together a circuit for us on these photo tubes. And Ted bid $500, which was the price of the parts to go into it. His dad was a drainage person, and he recognized the potential of this thing right off, and so helped us in that regard. A picture of the early test to confirm the operation and the response of the depth and grade control system on the drainage plow to the laser being projected it was a little more than 100 feet away. We had the plow on a truck parked next to the curb by the Ag Engineering building in Ohio State. We put the laser beam more than 100 feet back somewhere before we got to that street back there, and projected it into the thing and tried it. And I remember one of us yelled, "It worked!" After that, to make sure the first time we'd actually fired it up so that we would manually control the height of the receiver to see would the hydraulics be operated to move it back into the center of the beam, and it worked. So this was the receiver on it with the control box. This was one of the box that controlled the hydraulics. I think I've got a picture of that opened up. These are the 2 filters that were used, and those are probably the most expensive parts that Ted had to buy for that. And he used he had a choice of 90 cycle or 150 cycle filters, and those were relatively cheap because they were used on all kinds of electronics. If we'd have wanted something like 200 cycles per second filter, then it would have been much more expensive. So, but 150 cycles seemed sufficient for us. This plow was mounted on our lowboy trailer, parked, and took up a little over 2 parking places alongside the Ag Engineering Department. It was close enough to get to, and we actually welded on this thing. We finished up some of the plow construction and mounting the laser system. This got us into trouble in Ohio State because these couple times every week. We were parked here for nearly 2 months, a little over 2 months. The students and the faculty would report to the police that our truck was taking up parking places, and so, but they couldn't move it, and we didn't move it, so we got to finish up the operation before we moved to the field. This, in our first lineup in the field, 1966, lining up the laser beam, I set it up so we could put it on grade at a given height above where we wanted to lay the test pipe. I call this a fake picture, because we set the laser beam and it aimed it at the camera, so it would show up as a bright light there and not at the laser receiver right there. If we'd have made it, lined it up with a laser receiver, you wouldn't have seen it in the camera. Well, this is a picture of our first field operation. In early 1967, the ARS Installation Division took a movie of installing the corrugated plastic drain tubing with the drainage plow being controlled by the laser beam grade control system. The final movie, shown as a TV short subject story, was 3 minutes and 45 seconds long, but it took us 2 days to film it. We always said, well, go figure. This was Vince Markley, who was one of the top film directors for ARS in Beltsville at the time, and we were really pleased that he was assigned to do the job. This is the film crew. I have to comment, I have no clue as to why I wore that kind of a hat for this kind of a movie. It was shown quite a number of times. After that first successful field test, we knew there was a number of adjustments needed to optimize the operation. I developed an electronic analog computer setup and program to simulate the dynamic automated operation of the laser beam depth and grade control system on a floating beam type drainage plow. And this became a part of my PhD dissertation. This is the analog computer. I actually used the two control boxes for the phototube receiver and the hydraulics wired into the circuit. We didn't have the logic capacity in the computer to simulate the electronics on these, and probably may not have been able to simulate it correctly, because these are analog devices, but they're also nonlinear devices, not easily simulated. The recording of this, or the operation of this, once you set this in operation to simulate it running across the field with grade control, it would plot for you what's going on, but it also recorded on a mag tape, and you could record one thing at a time, so you could. And I mathematically described the operation of the laser and the plow, the laser beam, and the position of the laser beam receiver on the plow was one of the most critical factors, trying to figure what was the best position on the mounting that receiver on the plow beam. We knew it was somewhere between the hitch and probably the center draft of the blade on the plow. And we've defined the beam length as from the hitch to the center draft is the beam length, and X is the distance back for the receiver. And this B minus X distance was somewhat correct. We found eventually this X value being 5/6 times B, so this being 5, this being 6 of the B length was about the optimum we found through simulations, and this was confirmed in field tests as well. That was a little bit of a surprise to me, and it noticed from my original conception, it was not up near the hitch, it was back toward the blade. The forces on this thing, we had to mathematically math the soil resistance on the blade, and the pull on the plow at the hitch, and we didn't do anything with the dynamics of the feeder. We basically was on the plow blade. This is a system block diagram that you put together for this kind of a simulation, where you have the plow dynamics, you have the hitch motion coming in, the depth coming out, but those two influence the elevation of the receiver. And you have the input of the laser beam into this receiver. You have those controlling through the solenoid valves and the hydraulic cylinders back to the hitch height. Okay, and so it's a closed loop type feedback loop. The mathematics in the plow, dynamic analysis was fairly complex. It was a nonlinear equation. This by nonlinear, I mean this is it has h values in both sides of the equal sign, and you can't simulate it. There's no direct solution. So the only way to solve this at that time, in the late 1960s, was on an analog computer. And there was no way of doing it on the digital computer at that time. And later on there was, but not at the time. The only way to solve this was on an analog computer. But the forces were mathematically described. The most critical operation here was to simulate what happens with the depth of plowing. That's the D value here, and the height of the hitch for the control. This is the analog computer circuit. Now, I'm not going to go into this in detail. This is a typical, fairly complex analog computer circuit. It was the details on this, and anybody's interested in details on this, they can be found on the website in the research stories I've written on the laser beam development. Those can be viewed or downloaded from the Transforming Drainage Project website, and it's cross-referenced to my PhD dissertation, which includes all these details, and it's cross-referenced. And that PhD dissertation is digitized and is also available on that same website. So the details of this kind of thing. At one time, I had all this circuit totally memorized and knew what everything was precisely. The kinds of things we looked at, as I said before, you could only look at one thing at a time to record it on magnetape, and then but the neat thing about the computer simulation, you could repeat it like going over the same ground multiple times, where in the real world, once you go over the ground, that's it. You can't go back over and get the same input back to the plow. But on the analog computer, you get the same ground surface every time, and then record something. We did the ground surface roughness, the speed of the ground travel, the laser receiver position on the plow, could change that for each one, the dead zone of the laser receiver, the distance between the top row and the bottom row of the photo tubes, the hydraulic cylinder speed of response, the hydraulic valve, whether it's an on-off type or versus a two-stage valve or a servo valve. So all of those were simulated and looked at to optimize the control. I did what I called a show and tell. The administrators always, when you get something like this, the administrators always want to see it. The visitors want to see it, and it's almost like a politics in a way. Dr. Wadley was the division director out of Beltsville, Maryland. Bill Rainey was the chief soil scientist with the Beltsville group. Dr. Bob Stewart, he was our Ag Engineering Department chairman, and Dr. Schwab, my advisor. And here I am doing the show and tell, so to speak. I guess that was the days when I used a flat top hair top before. The first field demonstration of a laser plane system, and of course the guy that ended up uh, putting that circuit together for us, the phototubes, uh, met with an individual, Robert Studebaker, that was working on a laser beam system as well for land grading equipment, uh, but he was having trouble with the receiver end. But he developed what was called the laser plane system, a BASI system, something we were looking at doing long term. Our project was to use a laser line, and thought if we could control from a laser line, then we could rotate the beam into a plane and slope the plane for the field. But we never had to go to that stage of the project because Mr. Studebaker developed that concept into what he called the laser plane system. And he formed a company with Laser Plane Corporation, and him and Ted Teach went together with the company. But they had a commercial version of the laser plane system by 1967, after we successfully tested this thing on the drainage plow. And the first demonstration of that was in the fall of 1968 at the Ohio State Farm Science Review. This is the concept of a laser plane system was rotated into a beacon. The laser is projected vertically into a rotating prism that circles, and so it can operate several machines in the field at the same time. You slope the plane for the grade of everything. So the plane can be sloped this way and this way too. So every place you hit it, you're going to be on the right elevation or the right slope at a given height. The laser was typically set 10, 13 feet above the ground surface. Multiple machines in the same field on the same system. For the first demonstration for the use of the thing, there's no plows to put it on other than our research plow, was a tile trencher, and the receiver on the machine there. The other thing was interesting about this is a one-man surveying operation. Always with surveying, you always had to have somebody to transit the level and somebody with a rod. Well, now with the electronic sensor on the rod, you got a one-man surveying operation with a laser plane system. This is the system and demonstration form at the Ohio State Farm Science Review in that fall of 1968. Set up, it was a kind of a central location for the transmitter, and you could lay all the drains without having to move this transmitter. This one was set up and battery operated. A lot of times they use a truck, and the battery off the truck is sitting next to this thing. There's another closer view. There's a rubber-tired spiker trencher, wheel-type trencher, operated fairly fast, probably in the neighborhood of 40, 50 feet a minute for laser control. Some of the early corrugated pipe stringer handled coils of 4-inch pipe. These coils were typically 250 foot length each. This was one of the early type of stringers, and later on they became much larger coils. And there was the spiker trencher. This also brought out the administrators of ARS as well. Dr. Van Doren was my branch chief. He wanted to see this operation, which is always a part of the show and tell as well, if you want to keep your research funded. He was a soil scientist, not an engineer, so it took a little bit of extra explanation to explain this thing to him. And about this time, or soon after, the 1968 Ohio State Farm Science Review and the first laser plane system field demo, the trenching machine manufacturers in Canada, Europe, and US began introducing models of higher speed trenchers. And they're trying to compete against the plow. The trailers, wagons, chariots, and transporting drain tile in the field site to speed up the drain installations. And so some of the ones I showed earlier, there were more and more of these things, new high-speed drain plows were being, they knew that the high-speed drain plows were being developed in Canada, Holland, and Europe. None in the United States at that time, and really none now. Coiled tubing was rapidly becoming more popular and widely adopted by contractors and farmers. And so the clay tile recognized that their market was changing. The high-speed turbo-powered wheel trencher. This was really could operate quite fast, and it was a challenge to feed clay or concrete pipe to it, but corrugated pipe was could be installed with this fairly fast, and so that was the competition that was coming out. There was others kind of seeing this thing was kind of like a high-speed buzz saw, formed design as I recall, and back up here. The contractors called this thing the mudslinger. You notice this guy looks like he's ready to duck because if it was a little sticky, it could really throw clods back here. It was a really high-speed wheel. So the hose chain trencher, the German manufacturer, high-speed machine, became very popular, and it was laser controlled. And we developed what was called not by me, but by contractors saying the ARS Big Red Plow, and from 1969 to 1971. No. There we go. This is a preliminary drawing for the first design for the ARS drain plow with a hitch point on the push arms of the dozer blade. Right there. A top view. From this, I decided that the toolbar was way too wide in this thing, and so I needed to modify the design. And my professional moves with ARS over the years, I've lost the total set of drawings, and these are the only two I had left. But we redesigned it, and this shows what we did. They moved the beams and over the tracks so the toolbar could be narrower, and hitched the plow behind the dozer blade on this. This was a D8 cat. This plow is capable of 5.5 to 6 foot depth of operation. The reason for developing this plow was brought about by a talk I gave in Indianapolis to a drainage contractors group one time, where we had pretty well decided that the corrugated plastic pipe plowed in with a laser grade control was the way that the industry should go. And I recommended that the industry give serious thought to having a plow developed for installing the corrugated plastic pipe with laser control. And but I mentioned that to do that, the plow ought to be designed to go deeper than our research plow, because it would only go about 34 inches deep with our old modified mow plow. And a contractor in Indiana, one of the senior contractors, well-respected guy that I knew from several meetings before, stood up and asked me how deep it should go. And I mentioned to him that, well, I felt it ought to go probably 6 foot deep. Not that the drain should be installed that deep all the time, but if you got a bump in the profile that you could get through it without having to level it out ahead of time. And he stood back up after sitting down, said, yeah, Jim, I think that's crazy. I don't think you can do that and control grade. But it really set me back. I was thinking that may have killed the whole idea of plowing in corrugated drains. I convinced ARS after several discussions with them and a couple of trips to Washington to make my argument that we develop a plow that would actually go 6 foot deep and prove that it would control grade. and so I developed the design for that. And it took some more effort to get the money to build it, but we did. And I had the industry build the plow for us. This is a view of it from the rear, showing its width. It still was about 11 foot wide that way, but it functioned extremely well. The prototype plow. This was the prototype. Not we wouldn't actually didn't recommend this design because, and I'll talk about it a little later as to what I meant by the recommended design. But this was at a field demonstration in Monticello, Illinois, sponsored by the Caterpillar Tractor Company. When we had this plow developed or manufactured, I had anticipated that to get a D8 Caterpillar from military, either Army or Air Force surplus property, because we had, to that stage in our project, had received at least 2 D4 cats, 1 D6 and 1 D7 cat from military surplus. But when the plow was about 3 months from being completed, I still did not have a tractor to mount it on. And so I contacted Caterpillar Tractor and see if they could help, and they were very helpful. They donated this plow for the purpose, and even hauled it to the plant in near Dayton, Ohio, to mount the plow on, and at their expense, not my project expense. I didn't ask questions about that, but a little later I called the Caterpillar representative I was dealing with and said, "Well, there's probably a catch to this, isn't there?" And he said, "Well, there's kind of a catch. Yeah." He said, "I had to promise our administrators here at Caterpillar that you would demonstrate that brand new plow at one of our field days in Monticello, Illinois in August 1971. So I agreed, yeah, we could do that, but I'll need some help because my technician, Norm Fozzie, is trying to finish up his degree right now." So he said, "Well, no, the Caterpillar will help on that." So they assisted in the whole operation. This was the field demonstration at Monticello. The setup of the laser transmitter in one site, one position, and laid all the drains in the site. At the second day, and this is actually a 3-day show, as you will. Second day, we were asked to slow down, or we were going to run out of fuel because we were laying drains at about 3,000 feet an hour. The drains were about 1,000 foot long, and we were laying 3 drains an hour, and with laser control. And it was really a slick operation. We had a lot of visitors from farmers, industry, and officials of all kinds there, Caterpillar officials, and we're very happy with it. The Jack Diamond with the Caterpillar company, and Bob Studebaker, who was the president of Process Equipment. He was also the president of Laserplane Corporation. He's the one that partnered with Ted Teach to form Laserplane. They helped in the field too. Jack was the one responsible to arrange for the donation of the tractor, and Bob Studebaker's company, Process Equipment, was the one that had the contract to build the plow. So they spent the whole time with us there in that field demonstration. They even rolled out the pipe. We didn't have stringer trailers at that time. They rolled out the pipe for the installation. I showed the pipe tube feeder that's built within the blade of this particular design. The drainage contractors kept asking how deep we're going. And Jack Diamond of the Caterpillar knew that my wife was a painter, so he dug out a paintbrush and some paint, and she painted on the back of the blade the feet, and every half foot up the back of the blade to indicate how deep we were plowing. and this was a picture. We were going about 4 foot deep. We didn't. We in fact the blade wasn't set to go 6 foot deep here. We didn't want the drains deeper than about 4.5 feet in this particular field site. Kids came along on this too because we were there for a whole week. This chain trencher was used to install 6 and 8 inch mains for the project. We camped right on the site with our travel trailer for that week, made it kind of a family outing for us. Then right after that first demo at Monticello, Illinois, the Caterpillar helped us, and we loaded it up and took it to the Ohio State Farm Science Review, the same place where the laser plane system had been demonstrated in 1968 on a spiker trencher. And this was the second demonstration of the ARS plow. There was just hundreds of farmers and contractors at that place. In fact, I'd operated equipment myself, and I was scared of running over somebody. There was just so many people on the site. This many contractors, farmers, and a lot of industry reps were there at the OSU field demo. There were a few other types of machines around to put the mains in and backfillers. Our ground speed, we had run some preliminary tests and said that we shouldn't be going more than 150 feet a minute to have good grade control. And at this site too, the drains were about 1,000 feet long, and we were putting three drains in an hour, so we did 3,000 feet an hour, and that included not laying drains in both directions, but actually turning around, coming back and out and draining, putting the drains in upslope, and so there was double pass. In a couple of places we used the trip back to compact the eruption of the soil. 1,000-foot drain. Generally, these farmers would start following us as we started to drain, but laying 1,000 feet drain at 150 feet a minute, they just didn't keep up. And so there was always that, when I turned around to go back, there was always people I had to be careful not to run over, because they just were generally talking to each other and not paying a lot of attention. This was an interesting situation. The Zor plow was something that had been developed in Canada. It was a kind of a research plow, yet it was almost like a Ferguson hitch, imaginary hitch type thing. They equipped it with a laser control and brought it to the Ohio State Farm Science Review. They demonstrated it in the field. This guy on the plow wanted to race, and I didn't particularly, wasn't interested in that. But one of Mr. Reed wanted to run the plow on one drain, and he asked me to ride with him because he had never driven a crawler tractor before. And so I was riding. When this operator seen that I wasn't driving the plow, he decided that would be a good time to race. And Mr. Reeves seen that he was overtaking us, and he asked me, maybe you ought to take over. And I did, but I told Reeves, I said, well, I'm not going to be going faster than 150 feet a minute, because that's our grade control. If he goes faster than that, that's fine, just let him go. But he blew his engine before he could pass us, and so that was the end of that. And it was one thing. It was probably a good thing, because if he'd had continued operation, we would have run out of field to put drains in for that demonstration that at the Farm Science Review that week. This was the Badger plow. That was a design coming out of England. It was a roller, but it was an imaginary hitch. The hitch on this thing was an imaginary point, virtual hitch point out here in front. It was really kind of an interesting design. I didn't use this type of design in my plow because I wanted a physical hitch point to be able to put the laser receiver at some position straight from the hitch, measured from the hitch to the blade. With a virtual hitch, you can mathematically figure it, but it was not obvious where the beam was being moved. So This one was at that Farm Science Review site about 2 months before the Farm Science Review, but for some reason it could not stay at that site before show at the Farm Science Review. But it was one that Dr. Ansley Eade, I showed a picture of earlier, is that had the optical telescope and radio control for grade control, is the designer of this Badger plow, and it was designed and manufactured in England. The laser controlled ARS plows installed in corrugated drains in Florence, South Carolina. After I moved from Ohio State to Florence, South Carolina in 1972, the plow had been shipped to Louisiana and then out to California and put in drains on ARS research sites and farm sites, and they shipped it back to me in Florence, South Carolina in 1973. I wanted to finish up some tests. We had it mounted on a D7E Caterpillar at that time. I had to cut. This was a shorter tractor than a D8, so I had to cut about 3 feet out of the beam length and then reconfigure it somewhat and put in a little more modern laser system on it than was on it at the original field demonstration. But this was a picture taken by ARS photographers out of Beltsville. I've always looked at this picture as representing the results of 10 years of research from 65 to about 74. The automatic grade control accuracy in the drain plow installation of the laser plane controlled drain plow was field tested here at that ARS research site. I was the director of this lab in 1974. Had about 6 students working for me. They hated the job because I asked them to probe down into the slot. We put this drain in without a pipe. It was a kind of just a hollow channel, but I also put it at a either level slope or a very low slope, small slope, and had them put this what I call a T probe down into the ground with strip iron, and feel the bottom of the trench, and it was 3 feet long, and put the laser rod on top of that and measure it and get the elevations up along the bottom. The bottom was fairly soft, and so I know that they actually probably punctured the bottom of the channel a little bit sometimes. But I tested it with 2 different laser receiver positions. This is a B minus X of 3 feet, and this is 13 feet. This would be up close to the hitch point, and the other one would have been back by the blade. And the standard deviation was always better for back closer to the blade. I ran a number of tests, and this is where the standard deviation of the drain channel for the laser position. As this one is about a little less than 3 feet ahead of the blade was the smallest standard deviation, and this is about negative plus or minus 2 inches at that time. If you got farther forward, the standard deviation was greater. The fluctuation between high and low in the channel. And so these were some of the early tests that we did on this thing. And by the mid-1970s, many additional innovative advances were made by drainage industry and drainage materials and handling and installation equipment. Larger diameter corrugated plastic drains and manufacturing fitters. New models of drain plows and trenchers, mostly from Canada, England, Germany, France, and Holland, but still none from the United States. The hose drain plow is a German manufacturer, is a single beam with laser beam control. This was a modified hose plow that I modified, that I had for a research project, and put a sloping plane, what I call a soil lifting plane on the blade, and disc back fillers, and a pipe feeder on top. Now this lifting plane reduced the draft on this plow about 30% compared to the original blade design. And the president of Hose Drain Plow Company from Germany came to the United States and asked me why I welded on his plow. And after explaining to him what advantage we've seen in that, he modified the design of his blades from that point on. I also show this one because of this hitch point up here. This one doesn't show exactly what I want to talk about, but the hitch point is up close, right behind the diesel engine. And that was something I had in mind for the big red plow when I designed it. I was planning to move the tractor seat and the fuel tank and put the hitch for that plow up behind the diesel engine on that D8 cab. And that's when I was thinking we could get a surplus tractor from military and make that modification to the tractor and put the operator on a platform off to the one side of that. The administrators in Washington were pretty upset with me even thinking that way, and instructed me that I was to use the Caterpillar tractor as it came from the factory and not to modify it. I had ignored their advice earlier when I was told that I shouldn't use the laser beam system, so I didn't ignore their advice twice. This is the inner drain plow. It's called a double link plow. It's a very good plow. A Holland manufacturer with laser. This was a laser automatic control on this one. It shows on the other side that an onboard reel for the pipe. This is PVC pipe that's being installed in Europe and probably in Germany. It's not polyethylene. This plow is manufactured in Canada, but born. It's also a linkage plow with an onboard pipe reel. This is the Wolf plow. It's also a double link plow, and it has a modern sensor on it for grade control. This is a fairly new model, and this is just an illustration of some of the other many applications for the laser technology that even though the early research was for on the drainage plows, it got expanded to other applications in all fields quickly. But the one that had tremendous impact was land leveling in the irrigated areas of the West. And this is nighttime level basin land grading in the Arizona area for rice production. They liked night operation here because of the tremendous heat, and heat from the surface during the day would make this laser beam fluctuate somewhat in the air turbulence, but at night it was very stable. They also set that laser beam at least 13 feet in the air to get it away from the hot surface, and they would. But this operation, somebody figured out the economics that it's modernized the land leveling operation in rice production areas to the extent that it saved tremendous amounts of money for the farmers and the industry, and it paid for any equipment they ever considered using. The laser technology was recognized by the American Society of Agricultural and Biological Engineers as a landmark. But Norm Fozzie and myself as research partners, we were both also inducted into the International Drainage Hall of Fame that's housed in the Agricultural Engineering Department at Ohio State. I was inducted in 1990 and Norm in 2003. Then in 2007, the laser beam technology recognized the three of us. This is Ted Teach from Laser Plane Corporation for the development of the laser beam grade control prototype. And the plaque was presented as a landmark, what they called the ASAB laser beam landmark plaque, one in Ohio State and one plaque in the Laser Plane Corporation office. This is a plaque itself dedicated in 2007. and is on display at Ohio State University. Today, the laser plane grade control systems are being upgraded to the RTK GPS system on drain plows, where the satellites are used to with sensors on the machine uh, for controlling the grade, and one on the tractor for automatic steering through the field. The RTK component is one to correct errors that's typically occur with satellites. So the sensors on the plow are reading the same, are being read by the RTK system that's setting at a known XYZ coordinate. And as this RTK unit reads the satellite, the position that the satellites say they're setting at, and it's different than where they're actually setting, they mathematically develop a correction factor that's radio signaled to the sensors on the plow to adjust their position so it's more accurate in terms of XYZ, and therefore the sensor's accuracy is within a centimeter level control, half an inch type of difference. So the accuracy of depth control and grade control is extremely accurate with this system using the ground-based correction. And again, this single setup can operate over the entire field. And the design of the machines on the machine is the drainage system is designed ahead of time, and the drain path is identified as coordinates to follow, and the drain depth is designed as the depth that the drain needs to be put in, or the elevation at different positions along those drain line paths, and the sensors have that stored in them, and it tries to match that as it installs the drain. So you really have a computerized system operating the tractor and the plow to install every drain line. So it's a modern system. The laser plane technology, though, was operational for 50 years after it was put out and used on drainage, and now it's being upgraded and replaced by the RTK GPS system on almost all drainage plows.